So I'm going to discuss here the analysis that we have so far of our Laves phase experiment done at the SANS instrument NIST, January 2010. And in attendance of the experiment were Julie, Sandra, Catherine, Mark, and Mike. So these data show on a log-log scale the intensity of the SANS signal as a function of Q. And there are three features that you need to know about. One is something I call the spike, which is basically an uptake of the scattering as you approach Q equals 0. There is a bump in the scattering, and then there is a bulge in the scattering. And these will be fitted with different functions. The overall fit is given by this black curve. A difference between the black curve and the data point divided by the standard deviation by the error bar, that quantity squared is the weighted residuals, and you can see those by the rose-colored plus signs, and if they're fairly evenly distributed, that's a good sign. This information here tells you the conditions of the particular measurement. So the 1FC means that the sample was cooled in a +1 Tesla cooling field, measured in a -7 Tesla field, and the measurement was taken with Q, the wave vector transfer, 90 degrees from the applied field. So in all cases, let's pretend the applied field is in the horizontal plane, and if you see 90 degrees, it means that Q is in the vertical plane. And you have to remember that the magnetization that you're sensitive to is the magnetization in the plane perpendicular to Q. So this would be roughly in the plane that contains the B field. Now if this had been 0, then that plane, Q would have been this way, and that plane of magnetization that we'd be measuring would be in the vertical direction. So this would correspond to the sigma plus minus domains, and with this value of 90 in Q in the vertical, that would correspond to sigma naught domains. I should point out that these data required two detector settings, a detector setting with a detector far away from the sample to measure high Q, very close to the sample to measure high Q, and a detector setting far away from the sample to measure the small Q. And then there was NIST, we used the NIST software in a region of overlap to scale the two together. This is a correct thing to do, provided the resolutions, I believe, if the resolutions are the same, which I don't believe is the case. And in fact, on the asterisk spectrometer at Lujan Center, we do not do that anymore because I don't think that's an appropriate thing to do. But that's something that Mark, Julie, and I can hash out at a later time. In any case, onwards, I fitted the data to a collection of functions, two Lorentzians here, given here, and a Gaussian function. Actually, the intensity is the sum of the square of the Lorentzian, which is consistent with Julie's paper that indicates that the static scattering, as opposed to dynamic scattering, goes as the square of the Lorentzian. And so one Lorentzian takes care of the spike, this bit here, which is in this case the blue line, and the other Lorentzian takes care of the bulge, which is the green line here. And then the Gaussian takes care of the bump. Okay, and so when I fitted this function, I assumed that this parameter, I should be A1 here, A1, was fixed at a value of a very large value. So we're essentially just saying this is 1 over Q to the 4th behavior. What we're saying is that because we can't measure to small q, we cannot measure the length scale associated with whatever scattering is giving rise to the domains that are giving rise to the scattering at small q. Those are presumably very, very large domains. In the case of this function here, we are fitting that length scale, which is roughly corresponds to 0.03, and that gives you a length scale of this whatever domains contribute to the bulge. So I optimize this function to minimize the value of chi-squared, which is those, to minimize the magnitude of those residuals. In this example, we are at a cooling field of 1 Tesla, measuring at +7, so this is roughly a saturated condition. And you'll see that the SANS signal is very weak. It is weak compared to what I'll show you later, but it's non-zero, which is interesting itself. Because remember, there is no empty can contribution to these data. So these are data taken. These constitute SANS signal from our sample, which includes both the thin film and the substrate. And this is a nearly saturated, we would have thought a nearly saturated condition. And you see the signal is quite low. It increases somewhat as Q deviates from the direction in the applied field. Increases more. Notice that we always see the spike only when we have a condition of Q perpendicular to applied field. And now we go to the exchange bias field for this case, and you see there's an order of magnitude increase in the SANS signal. So that's quite exciting. Now the other interesting point here is that when you cool the sample in 5 Tesla field, the exchange bias, instead of being -2, is only -1 Tesla. However, we found that the maximum of the SANS signal is still occurring roughly at -2 Tesla, which is very interesting, because what it's saying is that we've got to understand why it is that we see an enhancement of the SANS signal, which is information about domains, small domains presumably, that is independent of the exchange bias. So how can it be that the domains are not related to exchange bias? So that's something we have to reconcile, and I think we'll learn something interesting by doing that. So onwards. Now, what I'm going to show you very quickly, because these talk can only be 10 minutes long, will be a plot of the parameter. Each of these parameters is a function of those different field conditions. In this case, I'm plotting the amplitude of that spike, and you only see a non-zero value of that spike at the condition of Q perpendicular to the applied field, so 90 degrees. This is the A2 parameter, which is the amplitude of the Gaussian. What's interesting is there's fairly systematic behavior here as you go from 0 degrees between Q and the applied field to 45 to 90. You keep increasing the value of that amplitude for whatever domains are contributing to that Gaussian. It becomes more and more noticeable as Q becomes perpendicular to the applied field. So that's saying that the domains that contribute to the Gaussian have magnetization parallel to the applied field. This is information about the half-width. Again, there is some systematic behavior here as well. This is information about the position of that bulge, and it's pretty consistent about 0.003. However, when you get to the very high field, you see it starting to push to small q, which is consistent perhaps with the periodicity of stripes or whatever creating this kind of signal. Remember, a peak means periodicity. This periodicity becoming larger. This is now the amplitude of Lorentzian representing the bulge. Again, it's a systematic behavior. The error bars are very small here in this case. You can hardly even see them. These error bars represent the value, how large you can perturb that parameter and increase the value of chi-squared by the value of 4. The number 4, which is a 2-sigma error bar. And the fact that these are very small error bars means that the data are very sensitive to this quantity in the bulge, the amplitude. And this would be the half-width. Again, there is some systematic information here. So that, I think, concludes the discussion of the interim analysis of these data. And feel free to look at the PowerPoint presentation that accompanies this.